First question is, which are the important formulas used in unsteady state heat transfer process for lumped heat capacity analysis? Second question, solve one problem on lumped capacity method.
During heat transfer process, some bodies behaves like lump. That is, its interior temperature remains uniform at all times when the heat transfer process is taking place. And this is known as the lumped system analysis. And this lumped system analysis is applicable for unidirectional steady state process when internal temperature gradient is negligible. Now we know that we use the formula for unsteady state process when internal temperature gradient is negligible. Theta by theta O is equal to e raised to minus HAT by rho Cp V. Now we will understand this with the help of this diagram. Now when the initial temperature of the body at time t is equal to 0 is TO and the temperature of surrounding is TF. Then the temperature difference in between this TO and TF we will consider as a theta O. Then after time t, so when the heat transfer process is taking place, then after time t, its temperature will become T. Then the temperature difference in between this T and TF is known as theta. Now the ratio of theta by theta O is equal to e raised to minus h. So h is the convective heat transfer coefficient because this object is in contact with the surrounding fluid and this fluid is having convective heat transfer coefficient h, that we have to write. A is the surface area of the object because the surface area is in contact with fluid. T is the time. So here T is time in second. Then rho is the density, Cp is the specific heat and V, that is the volume of the object that we have to consider. So this is the formula that we have to use, and if we calculate the Biot number, then from that we can if there is this Biot number is less than 0.1, then we can say that ITG is negligible, and then only we have to apply this formula. Now we will rewrite this formula. So I will rewrite this as e raised to minus t divided by 1 upon HA into rho Cp V. Now this RTH, that is thermal convective resistance, which is equal to 1 upon HA. So again I will write here e raised to minus t divided by RTH, that is instead of 1 upon HA I will write RTH, and CTH is the lumped thermal capacitance, which is equal to rho Cp V. So I will write here as a CTH. So this is the formula that we have to use in case of lumped system analysis.
We will read the given question. A metal rod of 10 mm diameter, 1 meter long, originally at 400 degrees Celsius, is suddenly dipped in oil at 100 degrees Celsius, for which convective heat transfer coefficient is equal to 250 watt per meter square Kelvin. Verify whether lumped capacity analysis is applicable for this situation. If yes, using it, determine the time required to cool the rod to 200 degrees Celsius. Derive the equation that you may use. Use rho is equal to 8000 kg per meter cube, C 460 joule per kilogram Kelvin, K 70 watt per meter Kelvin.
Let us understand the given data with the help of diagram. Here the metal rod is given whose length is equal to 1 meter and diameter is 10 millimeter. Now if we observe the temperature, the initial temperature at time t is equal to 0, TO is 400 degrees Celsius, and here we have to find out what is the time t when this metal rod becomes temperature T is equal to 200 degrees Celsius. Now the surrounding temperature is given, TF is equal to 100 degrees Celsius. So we will say that the temperature difference, that is TO and TF, is known as theta O, and temperature difference T and TF is known as theta. Now we will consider this metal rod as a cylinder, and we will first find out what is its characteristic length L. So L is equal to V by A. So volume, that is, we will consider pi r square L divided by surface area. So surface area, perimeter into length, that is 2 pi r L. So if we simplify this, we will get r by 2. Now we will first find out Biot number, and we will decide whether this given question is applicable for lumped system analysis or not. So Biot number is HL by K. So convective heat transfer coefficient H is given, thermal conductivity K is also given, and L is R by 2. So R is 5 into 10 raised to minus 3. So we have to use the standard unit meter. So if we calculate this, we will get 8.9 into 10 raised to minus 3, and this is the value less than 0.1. So here, for this case, we can say that here this is the case for the negligible internal temperature gradient, that is ITG. And when there is negligible internal temperature gradient, then this is the case that is applicable for the lumped system analysis. Now we will use the formula. So formula is, we have to first find out what is the RTH and CTH. So RTH is 1 upon HA, that is 1 upon 250, area A 2 pi RL. So we will put the value, and it is 0.127. CTH is rho CPV. Rho is the density, CP is the specific heat, and V is the volume. So V is pi R square L. So when we put value, then we will get the answer 289.02. Now we will apply the formula. So theta by theta O. So theta is 200 minus 100 divided by 400 minus 100, which is equal to e raised to minus t divided by RTH, 0.127 into 289.0.2. Now if we observe here 100, therefore 100 by 300 is equal to e raised to minus t by 36. So here if we simplify this, then it will become 1 by 3. Now inverse of e raised to x is ln. So with the help of calculator, we will calculate ln 1 by 3, that is minus 1.09. And inverse of e, and this e is getting cancelled. So on the right hand side, it will become minus t by 36. So this minus is also getting cancelled, and t is equal to 1.09 into 36, that is equal to 39.5 degrees Celsius. So this is the answer.